Well, with this, we come to the prize talks, 4 of which are scheduled. The Stern-Gerlach-Medal, the Herbert Walter Prize, Gustav Hertz Prize, and Georg Simon Ohm Prize. And we start with the esteemed recipient of the Stern-Gerlach-Medal 2021. And that is because of COVID. He never had a chance to give his prize talk. What a pity. Joachim Ullrich is from Rhineland-Palatinate, a wine-growing region, and decided early to study geophysics in Frankfurt, did his Habilitation on ion momentum spectroscopy, and then moved to the US, Kansas, University of Missouri, became chairholder in Freiburg, and received the Leibniz Prize of the German Research Foundation. Became director at the Max Planck Institute of Nuclear Research in Heidelberg, and then moved on to Hamburg because of free electron laser opportunities, became head of the Max Planck Advanced Study Group of the CFEL, and also built a particular end station that, while not yet readily available to operate in Hamburg, was simply shipped to Stanford and collected eminent data. Well, when you have done all of that, what's your next career step? Yeah, take over a German National Institute of Standards, the PTB, Physikalisch-Technische Bundesanstalt, where he was boss afterwards, at the same time becoming active in various academies and committees. Particular, the new system of units goes back to his research, and he might mention it in passing. He received the 2001 Stern-Gerlach-Medal, which is the highest DPG recognition for experimental physics. And the ceremony is not here. Here it is about his research and the prize talk. And last but not least, while he was selected for the Stern-Gerlach Award, the prize committee was gathering, another committee was operational at the same time and selected him as president of the DPG, almost at the same time, both of which is not related, except that he's an excellent physicist, and therefore we look very much forward to your talk. Joachim, I sit down, you stand up. Heartily welcome.
Yeah. Thank you very much for the nice words. Thank you very much for coming, actually. And it's my great pleasure, it's late but not too late, to talk about reaction microscope, bubble chamber for atomic molecular physics. Now this doesn't work now, maybe closer, yes. So what I would like to talk about today is give you some impression how everything started, what the question was and still is, kind of, how to answer this question experimentally, which questions finally were answered, I cannot tell everything, and what possibly does the future bring, if I have some time left over. So it started all in the group of Horst Schmidt-Becking here. I was a young student, we were in good mood, as you can see, and in an excursion. And I did part of my PhD, actually, at the Beverlag in Berkeley. There you had relativistic heavy ions. This little thing here is our experiment at a big brain, so this was more for bigger experiments. And then my supervisor here with some, my supervisor here, does it go back? Does not. Now it goes. My supervisor here, Horst Schmidt-Becking, with fine adjustment with a hammer of the little experiment. And we looked on what happens if a relativistic heavy ion, uranium-92 plus or 75 plus, hits a single atom. And what happens is actually that in a single collision, you can remove up to 40 electrons. So how can a fast ion remove 40 electrons from an atom in a few septoseconds, below attoseconds, was unclear to us. Another question of this time was, and was actually done also in Berkeley, Why is a heavy ion so efficient for tumor therapy with heavy ions? So what you see here is a survival of cells as a function of dose, and the survival goes down if you have more dose in your body, in your tissue. But what you can also see is that at the same dose, the same energy transfer to the tissue, carbon ion, the lower curve here, is much, much more effective than a proton, for instance, at the same energy transfer, and it was very unclear what it is. So these were the questions which we had at those times, and more generally, we were also interested, this doesn't work so well, what is the correlated motion of electrons in atoms? What is the correlated motion of electrons in reactions? Now, and more generally, you may ask yourself, this doesn't really work. Can we observe elementary quantum dynamics, like the making and breaking of bonds in a molecule? What is the correlated motion of electrons, and so on and so forth? And then the next question you might ask is, do you really need to do the experiment? Can you calculate? And here I would like to cite Dirac in 1929. He said, 1929, the general theory of quantum mechanics is now almost complete. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And now it comes. The difficulty is only that the exact application of these laws lead to equations much too complicated to be soluble. And this is why we need benchmark experiments up to the present day, good for us experimentalists. Now, can we observe elementary quantum dynamics? What is the experiment? Okay, whenever you observe, you know, a quantum system, you disturb it, or you may even destroy it. So one approach to get the information is, you better measure the complete multi-particle final momentum stage. So whatever you can get at information in the final state, you should take. Now, how to answer experimentally, and I would like to give you a status of when I started my PhD. So you could say, okay, why don't you build something like our particle physics colleagues, kind of a bubble chamber or so? This is not so easy, because we are dealing in atomic physics, as you all know, with nanoelectron volts, microelectron volts, several hundreds of eV or so, and you need spectrometers. And that means, and the state of the art at that point was, for ion collision, for tumor therapy, for instance, where you remove these many electrons, just one electron could be measured at those times. So you have not much information on what's going on indeed. And part of my task in the doctoral thesis was to measure the ion instead, the charge state and the momentum, actually. I built this little apparatus here, which you can see here, position-sensitive detectors, and so on. And finally, I succeeded. This was recall ion momentum spectroscopy. I succeeded and got my PhD, actually, even though I had built something like a sophisticated thermometer at the end of the day, because the thermal motion of the target was disturbing a lot of our measurements. And so the next step then was, and this was then done, the PhD thesis of Reinhard Dörner, to cool the target. This is cold target recall ion momentum spectroscopy, cold TRIMS, as we named it that in these times. And it was just on top of a cryopump, so to say, cooling it cryogenically down. And then we were, for the very first time, able to measure, at least for a single ionization, do a kinematically complete experiment, namely measure the ion momentum and the electron, also the recall ion momentum and the projectile momentum at the same time. Okay, let me see. Der Große, yeah, very good. And this brought me then also to the first conferences. Now, for electron impact, things were not much better. So there were so-called E2E experiments, where you could indeed measure 2 electrons, which are going out with 2 spectrometers. Very difficult experiments, actually. And for photons, which is important for vision, for photosynthesis, for light switches, and so on, it was similar. So these were so-called gamma 2E experiments, which were just feasible because the synchrotron radiation facilities were bright enough at those times to do these experiments for the very first time. Why is it so difficult? Because you have a small solid angle and you need to disperse the electrons. So the combined probability is something like 10⁻⁶. So very difficult experiments. So at the same time, now it continued with two ideas for recoil-line momentum spectroscopy to make the thing much, much better. Namely, the first idea was to use as a target a cold supersonic jet. So we had a localized and cold target. And the second idea was to just apply a little electric field. Electrons are not disturbed, but the ions actually are all projected onto a detector. And if you measure the time of flight and the position, you get the full momentum of these ions independently where they really go. And this was a cold target recoil-line momentum spectroscopy, I would say phase 2. This was a kind of a breakthrough already, because now we had a 4-pi solid angle, excellent momentum resolution, ion charged state detection, and these detectors were multi-hit capable, so we could actually also see the breakup of molecules and dimers and things like that. Now, and the next step is now how to measure electrons, actually. And this brings me to a kind of a desperate night at GSI. We were experimenting with, we tried to do recoil-line momentum spectroscopy at high energies, and it didn't work. For reasons I cannot tell you, we had many, many weeks of experiments, and in this night, we thought, okay, let's try to get a different trigger signal. Let's try to capture the electrons. And we did wind during the night some coils to generate a small magnetic field and direct electrons onto our detector. And that was, a huge surprise. Things went automatically very quickly, so we had lots of data and so on and so forth. We were not aware that we have been building, and it was no intention on that we have been building a spectrometer, actually, a very nice spectrometer. Namely, in these combined electric and magnetic fields, the electrons are on spiral trajectories hitting your detector, and if you measure the time of flight and if you measure the position, then you get again the momentum, at least in a 2-pi solid angle, very often in a 4-pi solid angle. Excellent momentum resolution. For the very first time in atomic physics, we could measure electrons down to essentially 0 energy, milli-electron volt, which was absolutely not feasible before, and we could also apply detectors with multi-hit capabilities in combination with the recoil-ion detection. And that is what we then called, so we had multi-coincidences, and this is what we then called reaction microscopes. And the next picture shows you the first reasonable one, which we then really built with my little group then at those times at GSI. Now, and this was then really a game changer in atomic molecular physics at those times, because we can use all kind of beams at any energy, actually, and we can also use many, many different targets, including also magnetic optical traps and things like that, which has been done later. And you could place additional detectors, and you could have additional beams, like, for instance, laser-assisted collisions, and so on and so forth. Everything went very quickly and very easily, actually, one has to say. I would like to show you one picture of a more recent experiment at the free electron laser in Stanford. It was just mentioned because it's quite involved. So this is one of these machines which I was still involved to build it, actually, and design it. The FEL beam comes from the left-hand side. If you look inside this apparatus, then you see the big potential field generating plates here for the recoil ion detection and for the electron detection. And actually here in the forward direction, we already had additional detectors for scattered X-rays. And here we did a lot of experiments looking for the structure of molecules, looking for the structure of viruses and so on. Okay, so with that, I would like to show you which kind of questions were answered. And these were actually very, very many. And I could give you only in 10 minutes something like, or 15 minutes, something like a very, very small selection. These are all reviews, actually, which you might read or even not. So a very small selection. I start with a very simple case, showing you the power of the method. So photoionization, so everybody knows, so photon comes in, The photon, in this case, had 80 electron volts. It has a lot of energy, but nearly no momentum. The photon is absorbed by an electron, and the electron goes out with the energy of the photon minus the binding energy, 50 eV in this case, and has a lot of momentum. And as everybody knows, this momentum has to be compensated by the recoiling nucleus. And now with recoil and momentum spectroscopy, you can measure this distribution of the recoiling nucleus and get the full information actually for single ionization. And what you see, you measure the full momentum sphere, and what you see here is just a cut in one direction, and you see a dipolar distribution of these ions which are coming out here, and this is photoions, correspond to photoelectrons in a dipolar distribution, very good resolution, 10 microelectron volts. Then you see additional rings, and this is the photoelectron, and the photoion has less energy if a second electron is excited. So you see all the excitations, and inside, if two electrons are excited to the continuums, you see double ionization. And this is what we then saw here. So this is then also the sum momentum of both electrons automatically, 70 microelectron volts. So this shows you again the resolution. And now the question was, what happens here? Theory had big problems actually to explain that. Now, what obviously happens is that a photon comes in and the two-electron wave function takes this photon energy. So the sum of these two electrons have a dipolar distribution along the polarization axis, as you can see here. But then the two electrons have to go out out of the Coulomb potential, which is not so easy because they have not a lot of energy. And then, as you can see here from the next picture, you could see that they actually emerge perpendicular to the polarization direction with quite similar energies in order to come out of this Coulomb potential, and this is also due to dipole selection rules. Now, we have then explored also for the very first time this via electron impact double ionization, the three-body continuum, three-particle continuum. How do three electrons share their energy and angles in order to come out of a Coulomb potential by having double ionization, for instance, in helium at very low excess energy. So they have to share 25 eV, and how do they come out? And this was measured then by measuring all the particles. We could see which kind of energy, relative energies they have, which kind of relative angles they have. And one dominant configuration is that these three electrons go out with the same energy and have the same always 120 degrees of angle in between them. So because this is the only configuration to some extent, if you go very close to threshold, that they all can emerge out of this Coulomb potential, out of this black hole in the middle. And we did find another configuration where one of the electrons was faster than the others, and the other two go back to back. So this was very difficult experiments feasible for the very first time at those times. Single photons hitting a dimere. And there was a prediction in 1997 by Lenz Sederbaum and his group on the so-called interatomic Coulombic decay. At those times, not clear whether it really exists. So this dimere, a neon dimere, has a long bond length and a small binding energy of 1.5 millielectron volts, van der Waals binding. Now, if you come in with a photon and just ionize the 2s shell, as you can see here, then an Auger decay is energetically forbidden in this case. What can you do as this dimere here? What can happen is that an electron from the 2p shell goes to the 2s shell, but transfer this energy actually to his neighbor atom via a virtual photon and throws out an electron on the other side. Finally, you have two neon atoms, two neon ions. You get Coulomb explosion, and by the Coulomb explosion energy, you get the wave function information, the distance actually. All of that could be measured by the group of Reinhard Dörner and others. The Coulomb exploding two nuclei plus the electrons and you could then see for the very first time the photoelectron, the first photoelectron up there, and these ICD electrons, and could compare it to theory. So this was the first demonstration that this thing really works. In a later experiment, and I don't go into any detail, in pump-probe experiments at the VUV FEL in Hamburg, even the time dependence could be measured, 150 femtoseconds plus minus 50 femtoseconds for the decay of this ICD. And very recently, or quite recently, this ICD was measured actually also in dimers and in a benzene dimer, and this comes very close now also to biological systems, because in radiation therapy, it is probably one of the dominant reactions actually to get, if the energy transfer to a system is very small, that then you transfer it to a neighboring atom and the thing explodes, for instance, in a DNA. So these experiments still are going on. Now, this were, this is difficult here. So these were single photons. And now I come back to these heavy ion collisions, actually. This can be explained in the Weizsäcker-Williams picture from 1934, why it's so efficient by the impact of virtual photons. And these experiments we could do for the very first time at GSI at those times when it was just operating. We had 1 GeV per nucleon uranium-92 plus, hitting a helium ion. We are just in the moment looking for single ionization. So the ion comes from the left, we look on the collision plane, the recoiling ions are scattered under 90 degrees. You would expect that for a distant collision, but then it comes, very low energies actually, even if this very high energy collisions, the projectile is nearly not deflected. So it's not kicked to the side like in a billiard goal. What happens is, this is going straight on, nanoradian. What happens is that the momentum is taken by the electron or vice versa. And this reminds you very much on photoionization actually, if you would come in with white light. And this is exactly the Weizsäcker-Williams picture. What you do is you calculate the electric field in the transverse direction as a function of time at a certain impact parameter, as you call it. And then you see that this field is rising to very high levels, actually 50 atomic units, in very short time, 0.3 attoseconds actually, and much shorter than the classical revolution time of electrons in the atom. You then make a Fourier transform of this very fast field, half-cycle pulse, you could also say, and then quantize that so that you end up with a field of virtual photons hitting your atom, actually, and simultaneously talking to all of these electrons, bringing them out into the continuum with a lot of energy transfer, but nearly no momentum transfer. The projectile just goes straight on, and this is why you can so efficiently actually ionize these by highly charged ions. It's very efficient, it's very soft, and these soft electrons are then very effective for further double strand breaks, and this is why it's so effective for tumor therapy. We had single photons, virtual photons. What about two photons? Also predicted very early on by Maria Gebert-Meyer in 1931. And these experiments could then actually be done in a very clean way at the free electron laser in Hamburg, using VUV photons, actually. And this is shown here. We had a dedicated experiment in Hamburg. Another one, which is actually for a lithium MOT, magneto-optical trap, to look for 3 electron processes. And here you could really explore the interactions of few photons with few electrons. I just want to mention it, but don't go into any detail. So obviously, if 2 electrons, 45 eV each, photons, sorry, have to coordinate their action, so to say, to bring 2 helium electrons out, which are bound by about 80 eV. This is one of the most simple 2-electron processes which you could imagine. Could it be calculated by theory? Yes, there are some papers, not complete, and there are some more. So very simple process, and there was a lot of discussion at those times. And we could do a lot of benchmark experiments, and I don't go into any detail. And there is also reviews written on free electron lasers, new avenues in molecular physics and photochemistry. Now, this brings me then to the last part. If you have not few photons, but very, very, very many, and this came up when the laser intensity was extremely high then, in the 20s or so, then you switch from the photon picture to a field picture. So you have an oscillating field in the laser field, and the electron finally can tunnel out in this in the maximum of the field. The electron can tunnel out. And here you can see the intensity as a function of ion rate, and you see very clearly that the tunneling theory, at least for single ionization over many orders of magnitude, does very well. So you don't need the photon picture anymore. For double ionization, it looks good up there, but then there was this famous knee, which was discussed over many, many years. What's going on here? This was called non-sequential double ionization, and you had orders of magnitude difference due to electron correlation. So electron correlation finally makes the energy transfer, or causes two electrons going out in a very efficient way, obviously. It was not clear what it was. So different mechanisms were discussed, like for instance, a collective tunneling, or a so-called shake-off. One electron goes out fast and the other one finds itself in the continuum, or a kind of a recollision. So one electron goes out, comes back to the ion, and electron impact ionizes the ion actually at that point. And now we did experiments just measuring the recoil ion. And in the sequential regime, we find a distribution along the polarization axis, but mainly centered at zero momentum, whereas in this regime, you find a double hump structure. And what is the explanation? The explanation is that the ion, when it is created in this field here, it acquires momentum according to the phase in the field where it is born. So if it is born in a part, like for these processes here, where the field is strong, the ion momentum is small, and if it's born when the field is actually close to zero, when this recolliding electron comes back, the momentum is large. So you could distinguish for the very first time these processes, and actually you get a sub-femtosecond phase measurement by the ion momentum, and this then later on, so this was the only thing which was left over, so to say, so it was a clear explanation now, and this later on was then the basis for these beautiful experiments by Ursula Keller and others on atto clocks, because you can use the ion to get a clocking, sub-cycle clocking, or finally also atto science. Now, with that, I would like to conclude, actually, and I think my time is over. Not yet? 3 minutes? Okay. Okay, then, because, yeah, okay. Very good. What does the future bring? So I think the future for this technology is very bright. Actually, this was... Now, everybody is awake again. Naja, the thing is, okay. Future is bright, namely, why? Actually, in the very sense of the word. Why? Because we now have sources. What happens now? No, I'm fine, I think. Yeah. It was me. It was actually me. I was pushing the wrong button here. Don't care. Okay, we will have these heavy ions at megahertz repetition rates in the future. The same is actually also true for for optical fiber lasers at megahertz, so highly intense lasers at megahertz repetition rate. The same is also true for attosecond pulses at megahertz repetition rate, and also inter-terahertz pulses. And here I would like to mention one very beautiful experiment, actually also with a reaction microscope by Jens Biegert and his group. So he had a small molecule here in a terahertz laser few cycle pulse. And this is, let me see. Okay, OCS molecule, and at the beginning of the pulse, one electron is tunneling out, and this causes some dynamics in the molecule. So as you can see here, it seems to bend actually. Now this first tunneled electron now comes back with a high energy, with 900 electron volts, because in the terahertz field it can acquire a lot of energy, and then is scattered at this molecule, at this bent molecule. So you can now do electron diffraction with a single electron being scattered back. Very beautiful experiment, I think. And indeed, they could then measure the bond lengths with a sub-angstrom resolution, as you can see here, by these scattered electrons. They could also detect this bending angle, and very interestingly, the time scale when this electron comes back is defined by something like a few hundred, 200-300 attoseconds. So this shows you now the potential, actually also with other radiation facilities coming up, what you really have to look for molecular reactions in the future. So sub-femtosecond time and picosecond position resolution, and then this, I'm very much sure, can also be done now by the next generation of free electron lasers, which are operating at megahertz, for instance in Stanford. So a new machine is just being built up there. And so this means, for me at least, that what you have seen now and what you can read is just a little prelude, because these reaction microscopes live at megahertz repetition rates. They like it, and statistics is very good. So we will see a lot of results, I'm sure, in the future. And that brings me then really to the end. I would like to thank first my group, which here you see in 2012 in Heidelberg, Robert Mooshammer, Alexander Dorn, Klaus-Dieter Schröder, the Heidelberg group in 2012. This was the advanced study group you mentioned. I would like to thank Sascha Epp, Faton Krasnicki, Lutz Foucault, Adam Rudenko, Daniel Rolles, and Ilme Schlichting. This was a camp group in Stanford, and here actually this was a beautiful time. Every experiment you did was something new to measure. Yeah, then many other people contributed over the years. I'm very grateful to the teams at these big facilities at GSI, LCLS, DAISY, SCSS, and SACLA, actually, and finally, the different universities at Frankfurt, Freiburg, Helmholtz Society, Max Planck, DFG Leibniz program, and BMBF. And last but not least, also to Horst Schmidt-Böcking. And these are the pioneers, Reinhard Dönner, Robert Mooshammer, Volker Merkel, and Horst Schmidt-Böcking. And I would like to thank you for your attention.